Welcome to The Explainer. Today, we're going to peel back the cover on your smartphone, your computer, heck, your entire modern life, to get a look at the tiny, almost magical things that make it all work.
Okay, let's dive right in. We usually think about electricity in really simple terms. It's black and white. You've got materials like copper that are conductors. They let electricity flow through them like water in a pipe. And then you've got insulators, like the plastic on that copper wire, that just stop electricity cold. It's either on or it's off.
But what if that wasn't the whole story? That one question, that idea of exploring the gray area between on and off, is what led to an absolute revolution. It led us to materials where we can precisely control their conductivity. And that ability, well, that's the key to everything. So here's the game plan for today. We'll start with that magic material, then see how we can control it with precision. From there, we'll build a one-way gate for electricity, use that gate to tame the power from our walls, and finally assemble the ultimate electronic switch that powers all modern computing.
All right, first things first. It all starts with a special class of materials like silicon, known as semiconductors.
Okay, so check this out. This is where it gets really cool. On the left, you see silicon at absolute zero. We're talking unimaginably cold. And when it's that cold, all its electrons are totally locked in place. It's a perfect insulator, nothing gets through. But then, look at the right. Just add a little bit of heat, a little energy, and bam! Some of those electrons get knocked loose. Now they can move around, and that creates a tiny little electrical current. And here's the kicker. When an electron leaves, it leaves behind what we call a hole, a spot with a positive charge that can also move around.
Now, being a weak conductor, that's not super useful by itself, right? The real game changer is when we figure out how to control this stuff with insane precision. And that process, well, it's called doping.
So one way we can do this is by adding a tiny amount of an impurity like phosphorus into the silicon. Now, phosphorus has 5 electrons on its outer shell, but silicon only has 4. So when they bond, there's this one extra electron just kind of hanging out, with nowhere to go. This gives us what we call an N-type semiconductor. N for negative, because of all these extra free electrons just waiting to carry a current.
And you can probably guess what's next. We can do the exact opposite. This time, we add an element like boron, which only has 3 outer electrons. So now, when it bonds with silicon, we've created a missing electron, what we call a hole. And this hole acts like a positive charge. So we call this p-type. P for positive. Makes sense, right?
Okay, so now we've got these 2 different flavors of silicon, one with extra electrons and one with extra holes. But the real magic, and I mean real magic, happens when we stick them right next to each other. This creates something called a p-n junction, and this little thing changes everything. If we hook up a battery like this, positive side to the N-type, negative to the p-type, something kind of weird happens. The battery actually pulls those free electrons and holes away from that middle junction. That barrier between them gets wider and wider, and boom, no electricity can flow. The gate is slammed shut.
But watch what happens when we just flip the battery around. Now the positive end pushes the holes, and the negative end pushes the electrons right towards the junction. They smash through that barrier, meet in the middle, and just like that, the current flows super easily. The gate is wide open.
So what we've just built, this p-n junction, is a diode. And its whole job, its entire reason for being, is to be an electronic one-way street. It lets current flow this way, but blocks it completely from going that way. Simple, but incredibly powerful. Okay, so a one-way street for electricity. Why is that such a big deal? Well, it's because the power coming out of the outlets in your wall is a complete mess. It's this chaotic back-and-forth current that our delicate electronics just can't handle. This is what that wall power looks like. It's called AC, for alternating current. And you can see the voltage is just constantly flipping from positive to negative, over and over, 50 or 60 times a second. Your phone would get absolutely fried by that. What it needs is a nice, steady, stable flow in just one direction. That's called DC, or direct current. And this is where the diode becomes a superhero. We can use 4 of them in this clever little setup called a bridge rectifier, and it basically performs electronic wizardry. No matter which way that crazy AC current is flowing, the diodes are like traffic cops, steering it so it always comes out going in the same direction. It literally takes that negative part of the wave and just flips it up to be positive. So cool.
So now we've got a current that's always positive, which is great, but look at it, it's still super bumpy. It's not a smooth ride at all. So we add one more simple part, a capacitor.
You can think of it like a tiny, super fast battery. It charges up on those peaks and then releases that energy to fill in the valleys. And just like that, we get the clean, smooth DC power that all our electronics need to live.
All right, so we've built a one-way gate. That's huge. But now for the grand finale. If the diode is a gate, then the transistor, well, the transistor is like a smart, fully controllable faucet for electricity.
These little guys with their 3 legs are transistors. You can kind of think of them as 2 diodes stuck together, back to back. And it is no exaggeration to say that this is probably the single most important invention of the 20th century, period.
The idea behind it is actually pretty simple, but it has these profound consequences. A transistor lets a tiny, tiny electrical current on its middle pin, that's called the base, control a much, much bigger current flowing between the other 2 pins.
And this ability to control a big flow with a tiny one gives it 2 superpowers. First, it can be an amplifier. You put in a weak signal, you get a strong signal out. That's the heart of all radio and audio tech. But the second one is even more important for our world today. It can be a switch. That tiny base current can turn the big current completely on or completely off, instantly, with no moving parts, billions of times a second.
Just stop and think about that for a second. A switch, a tiny switch that can flip between on and off, representing a 1 and a 0 in binary code, billions of times every single second. Okay, now hold that thought and take a look at this number.
That is roughly how many of these little electronic switches are crammed onto a single modern computer chip. I mean, every single thing your computer does, every key you press, every pixel that lights up on this screen, every bit of information it processes, it's all happening because billions of these tiny transistors made from doped silicon are flipping on and off in perfect harmony.
And there you have it. It all started with this weird material that couldn't decide if it wanted to be an insulator or a conductor. From that, we built a one-way gate, and from that, we built these unbelievably fast switches that are literally the foundation of our entire digital reality. It's just an incredible journey, from a simple grain of sand to the supercomputer in the palm of your hand. Thanks for watching.